Okay, hello everyone. So this is our second week of this course, Applied Machine Learning, and today we will give you the first case study, which is about machine learning in primary industries and mining. So today we invited Asan come here to present some of his recent works, and he will talk about basically how did he use machine learning in primary industries like winery or mining. And Hassan is a senior research fellow at the Australian Institute for Machine Learning and a principal researcher at the Center of Augmented Reasoning at the University of Adelaide. He was awarded his PhD degree in 2015 in computer science from the ANU, and he also has extensive experience in deep learning for a range of applications of machine vision and language in agriculture, mining, defense, and so on. And his past experience in the industry includes Microsoft and NEC. He has been a research scientist and founding member of DeepSight X, which is a AI mining company who won the second prize in the Global Mineral Discovery Challenge in 2019. Okay, so let's welcome Asan, and Asan can start to share a screen.
Thanks a lot, T. So today I will talk about some of the industries that can be impacted by AI and how AI is revolutionizing these fields. I particularly focus on the application of AI in mining, as she suggested, but also a few applications in oil and gas and even bushfire detection that I think is kind of related. In this talk, I will talk about improving existing industries. Some of them are more conventional and traditional industries that have impact for all our lives. And these are primarily the industries that have interactions with the natural resources. So we have to be very careful about using natural resources and optimizing any use or any aspect of these technologies can have great impact not only on us, but also on our children and next generations to come. And it allows us to basically utilize the existing data that has been collected throughout the history of these applications. So AI can benefit these industries as well as many others by three areas. And I think it's important for us to look into this because sometimes when people hear about AI, it feels like it's a scary thing that comes to just eradicate their jobs. And while it could be true for some of the repetitive tasks that people do, it's not certainly true in many cases because it creates a lot of new jobs and it makes a lot of jobs easier. And that's the point that I hope I can communicate as well in the case studies that we have today. So AI can, of course, augment our work habits. It can act as an assistant to the existing work processes and pipelines that we have, and it basically can help us with complex parts, complex tasks, and in many cases we hope that it helps eradicate a lot of rudimentary tasks, the simple tasks that doesn't really requires a lot of creativity, a lot of challenges, and we leave the creative part to human beings. So AI helps basically, it can have a direct impact by restricting or recommending new actions, or giving us insight into how things work. It can basically provide an evaluation of how the behaviors so far has been, and it can help with improving different aspects of the work. For example, it can make sure that the safety requirements for a job is satisfied. So the AI algorithms basically start with data, and data is an important aspect. And data is an important aspect of making these technologies possible. And usually, the way that the data is collected, or we hope that it helps, is that we start with the existing data, and we build a model upon that existing data. With that with that model, we could collect new data, and using that we can refine the model. So many of these industries, as opposed to prototypes that you can see outside, they are really you should have this kind of thinking as part of the process of how these technologies would be integrated. So it's not like they would basically be replacing every aspect of the problem, but they could take the existing data and improve upon that, and then with that you get new data, you get new insights, and you can build better and more improved models and technologies. So why do we talk about AI now, or why do we feel like it's a good time to incorporate AI at this stage? So a lot of, as I said, a lot of AI technologies really depend on data. So they are data-driven technologies. So part of what made it possible for us to think and talk about AI at current stage is that the data has been, a lot of data has been collected, and there have been a lot of revolutionary new technologies in terms of sensors and new data collection methods. So when we have these new data collection methods, it allows us to really have a better grasp of the reality and what's going on behind the scene, or in different aspects of the applications that we are looking at. We have been able to secure and mature the storage technologies. So the data that was collected, maybe in different stages, in different, I guess, in the past, data could be collected in a shape or form, but we couldn't store a lot of data, and that was why a lot of data would be discarded. But now we have storage technologies that allow us to, for example, using cloud, to store a large volume of data without any problem. So we can collect real-time data, we can store a lot of them, and we can retrieve and access a lot of it quite easily. There are standard protocols, there are basically mature technologies that allow us to access these large volumes of data. And the other aspect that make AI possible today is that we have better computing power. So we have GPUs and CPUs today that are faster than ever. We can parallelize a lot of the algorithms using GPUs, and our CPUs are really good for doing single task methods, that single task operations that we really need for the AI pipeline. And at the end, we have now better algorithms. So while a lot of technology that AI relies on has been developed maybe far back, a lot of new advances make those principal theories kind of applicable today. So we can now use them in practical applications. They are now more efficient, more reliable, and we can use them with large data sets, so they can learn from large data sets. And this is one of the great aspects of the AI today. because the old method or traditional methods, they couldn't really utilize all this large data, and there was a ceiling to how much they could learn. But now we virtually have a possibility of building very large models that could learn from very large data sets. So the point of using AI is really, of course, we want to do predictions, we want to do estimations, we want, but ultimately we want to get better insights. We want to get better insights into how humans perform. We want to get better insights in how certain industries or certain aspect of an industry really impact the yield or the outcome. And we want to get a better understanding of how we can get actionable insights, basically how we can get an outcome that we can rely on and make our next decision, and that decision is based on data rather than hunches and gut feelings and so forth. And you can see that there is a circle to it. So obviously you collect some data, and that data was generated by some intuition, maybe initially. We usually get basically features and models, they are combined, but in many cases we need to do some processing, some cleaning of the data, some normalization and so forth. And with that we get models, that AI models that would help us with going through this iteration, getting better insights, or getting better predictions in whatever we want to predict as the output, and move forward. And this is all basically a lot of it is done by supervised deep neural networks. So a lot of what deep learning methods that I mentioned, or machine learning methods that I mentioned, are basically utilizing this deep neural networks. And it's important to I'm guessing you guys have the background for it, but in a nutshell, it basically is a lot of parameters that connect the input to the output. And through learning, through getting a lot of data, you can basically build more robust path, more robust direct connections between these neurons and nodes that would give you some processing of signals in the input. It's also helpful for us to understand which signals in the input kind of contribute more to the output that we get. This becomes apparent in one of the instances that I will show, but this is one of the ways that we can get some explanation from otherwise black box models. You can see that there are some hidden layers. So we build these neural networks by stacking layers upon layers, and it's helpful because it gives us a more complex model, or a more complex relationship between input and output could be modeled using these multi-layered neural networks. And that is something that we humans really cannot do. So if the inputs are getting larger and larger, or the outputs getting larger and larger, the type of relationships that we can really easily investigate or understand are typically very small subset of those input outputs. And that's one of the reasons that the insights that we get, or predictions that we get with more conventional methods, are in many cases insufficient for today's technology. And these neural networks and the AI that is built on top of that is very is potentially is revolutionizing these fields. In these technologies, we talked about how important data is, but the reality is that a lot of applications where we talk about this type of data, the data is not really that clean. A lot of cases, the data is incomplete. So we can think of a lot of new ideas or a lot of new technologies, but a lot of them depend on data that we might not have. So when we talk about different steps or different aspects of the problem that we want to look at, it's important to know that there are a lot of missing data. Even the cases that we might think that there is data collected, when you really get your hand on the data sets that some of these industries have, there is a lot of missing data. There is also a lot of different versions. So that versioning could come from the first circle that we saw. Basically, you go through data model. So in a sense, even though they didn't have very advanced models, in many cases, because of different heuristics, different intuitions at different stages, there are different aspects of the data that has been collected, or different types of data that is being collected. So that's also important to know that when we are building the model, we might not have all the data that we want at different stages. There is also a notion of structured and unstructured data that might be combined. So unstructured data could be text, it could be images that are unannotated. And there are some structured data, the tabular data, the type of data that you might be able to find in an Excel sheet or an SQL database. So in many cases, the final decisions really depend on a combination of these different and fusion of these different data sources. So, and we want to utilize that obviously to train these AI models. The other thing that we have to consider is that while building the data and building the models is possible, the other aspect of this is that we want these technologies to be accepted by the practitioners, by the people in the field. So while we as outsiders or people with AI technologies could provide these technological advances, and they are basically being innovated and being innovative and incorporate a lot of those, but these technologies have to fit in the existing pipelines, the existing mindset of the people who are working in these technologies. And this is very important to really consider the steps that are needed to be taken for the human aspect of these for these methods. And for example, in mining that we are really looking into, it has thousands of years of history, and it has accumulated a lot of misconceptions, a lot of dogmas, and a lot of what is considered the expert opinion. So when you come up with a new technology, it is very important to take these expert opinions and these existing cultures into account when you want to influence and have an impact on this technology. And we can't really, in the instance of mining, we can't really function as societies without mining technologies, because we really need to know, we really need to have access to these resources, and these resources are finite, as we know, and through the years, through the misuse of them, we are basically we are basically removing the possibility of the next generation from really having access to these resources, and basically being take advantage of those. So for some of the technologies that we can incorporate in these industries are the ones that are really adapted from other applications. For example, in mining, we have all seen autonomous driving, and it has been showcased for civilian driving. But but there is a completely different scenario for using it in mining. Even though you can take inspiration from these applications, you can take a lot of the existing technologies that have wider application. But when you take it to the mining, there are a lot of new challenges and new things that you have to think about before really adapting them. For example, a lot of autonomous driving that's being built today, it relies on on-road and lane defined kind of constraint that you and it's an environment that you have cars following certain rules. But when you take it to mining, which is a very natural thing to think about, it's you don't usually have the roads, you don't really have the signals, so it becomes a bit of a different problem, even though the starting place might be very similar. So you come up with a lot of complexities that are problem specific. These problem specific aspects have to be basically incorporated into by using the expert's knowledge as a key, because when you incorporate expert knowledge, it gives you a stepping stone, so you can get usually better performance, but it also allows for better acceptance of the novel approaches, because if the experts feel like the technologies that are developed using AI are being helpful, then they are more accepting of the technologies, and the technologies really get incorporated into those industries much faster. And the other aspect is if the approach, because in many of these traditional in these industries that we want to talk about, there is a lot of existing knowledge and existing expertise. A lot of them, for example, relied on physics models. If you start to change these models, if you start to provide black box solutions, because they might not be explained by those physics models, there's a friction, there is a tendency not to really appreciate the outcome, and it has to be fully tested, because any error that your model could do, any uncertainty in the model's output, could have a huge impact, both financial and in many cases human disasters. So let's look at mining. Obviously, mining has been done for ages now, and it has been a very labor extensive industry. To a certain extent, it still is a labor intensive industry, because you still need a lot of human intervention, a lot of human decisions are required for these industries to work. From the very early stages that are about discovery of where you can probably find an important mineral or a useful mineral, to the area where you have to basically start digging and drilling, to basically building tunnels, to building the actual mine, to transporting what is excavated to a factory, for example. These are all areas where human intervention is needed. And as you can tell, it's a very difficult and also dangerous job to have. So any way that we can really incorporate technologies, incorporate machineries that can work autonomously without human intervention, we are making a huge, we are having a huge impact. So with the industrial revolution, obviously, mining has changed a lot. Things that were traditionally done by humans are now done to a certain extent by machines, but supervised by humans or operated by humans. And they have a huge impact in what we use daily on daily basis. Let's look at So we saw how a traditional mine looks like, and how a traditional mine, everything is excavated from down on the mine, and then carried up and then used in the factory, or transported to the factories. Let's look at how, for example, in current mining approaches work.
Hi, Essen, do you have sound for this video?
Sorry?
Do you have sound for this video? We cannot hear anything.
Yes. Okay.
Yeah, so because you have earphone or something.
Yes, let me see if I can. So do you know how I can change the settings here? Do I have to change the settings of the...
Are you using any headphone or something to?
Yeah, let me remove my
Yeah,
headphones.
you can just target the alt, yeah, remove it and use your computer or laptop to play it.
Yes, yeah. It might affect the how it sounds, but yeah, let me know how it goes.
Yeah.
The mining industry.
Can you hear it now?
Yeah, it works.
Yeah, thanks.
Is facing an interesting future with growing demand as well as severe challenges. Being traditionally a labor-intensive industry, the trend now is to vastly increase the level of automation. Here are some of the challenges facing the mining industry today. Local mining companies have become multinational giants, and mine sites are normally very remote, often with harsh climatic conditions. It's difficult to recruit and retain competent staff to run mining operations in remote places like deserts or mountains. Another challenge is decreasing ore grades. Mines are digging deeper and deeper to find ore bodies. As costs go up, so must productivity if mining companies are to stay profitable. Workforce safety is the most important challenge. In spite of efforts being made, accidents still occur, resulting in tougher regulations from the authorities. Workers' safety must be improved, especially in underground production areas. And people working close to heavy machines are also exposed to risks. How can we minimize accidents to ensure a safe production environment? Another challenge is rising energy costs. Energy efficiency and the tracking of energy consumption have always been areas of concern for the mining industry. The key for improving energy efficiency is a tight integration between the process and power areas of the plant. But this is not always the case. The last challenge is typical in many industries. On a site, there's a large number of independent equipment and systems. Each has its own information and interfaces. Operators and control room staff look at different screens and have only separate pieces of information at hand, no overview. We call this islands of automation. This lack of unity and integration goes all the way into the control room, making it difficult to decide in a timely manner. Let's take a look at a complete mine with a processing operation. It has 4 process areas where operators run their own machines. Not much communication or collaboration between them. No integration of equipment or systems either. Optimizing the complete value chain becomes a tough challenge. The key is having a full unified view of the production, from raw material to processing, stockpile, and delivery. An integrated solution helps close gaps in the value chain. For example, with good communication, the blasting and crushing in the mine can be optimized together with the grinding process in the concentrator as a whole. To summarize, the main challenges are safety issues, lower ore grades, rising energy costs, mines in remote locations, islands of automation and gaps in the value chain. Now to the solution. ABB strongly believes that the future of mining lies in bringing equipment, systems, and people together. And the answer is automation. Extended automation. This mine site has 4 separate areas run by local specialized operators. It's costly and less efficient. We want to bring them together, talk the same language, and be integrated into one system where all information is available. Local control rooms may still exist, but the trend is towards centralized operations. With modern control room designs, people with different roles can work together in the same environment. Barriers are torn down, control rooms are consolidated, and experts can collaborate in one place. Extended automation closes gaps in the value chain and creates a safe, reliable, and predictable production process. It also gives better visibility, from mine to concentrator, smelter, and stockyard. The result is an optimized operation from mine to port. The beauty of System 800XA is that all information is available to all users, locally, centrally, as well as for mobile operators with iPads or smartphones. The Extended Operator Workplace from ABB is a modern cockpit for mining operations. With 800XA, everything is integrated. Traditional process control systems, such as PLCs, DCS, and safety systems, and electrical equipment such as drives and motors, as well as production planning, maintenance, asset management, and documentation systems. 800XA can integrate different users, live video, voice and public address systems, web information, you name it. All information is presented in a uniform way, tied to physical assets. It can even include unmanned equipment, helping reduce the number of people working in dangerous areas of the mine. Bringing equipment, systems, and people together for a reliable, safe, and predictable operation. That's extended automation in a nutshell. Here are some practical examples. Let's start with asset management, a very important matter. There's a piece of machinery, and the operator has just been alerted by a predictive maintenance alarm that it will be needing repair soon. The operator can access the maintenance system and see all upcoming work orders. It's easy to add new work orders. He contacts the field engineer, who views the same information on his mobile device. Together, they decide on optimal maintenance action. Here's an example of how to control rising energy costs. In some mines, ventilation accounts for almost 50% of energy consumption. Mine vehicles emit diesel exhausts that have to be ventilated away. The automation system knows where each vehicle is, and all vehicle data, including emission levels, is communicated to the system. Ventilation is continuously optimized for actual need, and the airflow can be adjusted at any time. Minimizing energy consumption while preserving air quality means great savings. With the integration of process and power automation in System 800XA, energy usage can be measured in real time. It enables operators to detect energy thieves in any area of the plant. Need another example? What about increasing the processing plant performance in a consistent and reliable manner? In the processing plant, impurities are eliminated from the ore before smelting. The plant needs to react quickly to ore property changes. With ABB technology, this becomes possible. It tracks material movements and properties all the way from the mine to the processing plant. Ore properties are logged and represented graphically, eliminating guesswork. The information is available for other advanced applications, as well as to support operators' actions. Material movements are automatically synchronized with inventory management systems that look after the logistics and the supply chain. Finally, ore information is used by process optimization controllers. They use forecasts of the ore properties to make predictive adjustments to the grinding and flotation circuit. The result is higher equipment utilization, increased production, and lower energy consumption. Mining companies have become multinational giants, with mines scattered all around the world. With System 800XA, all information from local mines is also available and consolidated into corporate headquarters. This facilitates collaboration across mines. Production planning, resource planning, specialist support, inventories, spare parts, etc. can be optimized. By harnessing the full potential of ABB's extended automation, mining companies can raise their productivity and safety and achieve a more efficient and profitable mining operation.
So I think this video gave a very good intuition into how the mining industry works and what are some of the challenges. And obviously this is from one company that tries to provide some of the some form of solution, even though it's not really a comprehensive solution. It doesn't really incorporate a lot of AI technologies, but it allows for concentration and consolidation of data and centralized monitoring systems that can really take advantage of AI and advancements in the field. So AI in mining, in a nutshell, can be used in various areas. So one area is that I will show you an example of is exploration and discovery. So it has always been a very tedious and very difficult process to come up with places where it's financially viable to drill a hole and start building a mine. And in many cases, it was done in the areas where it's possible, it's sufficiently close to the surface, and you can really do an exploration or with some of the rudimentary or more traditional kind of equipments. But now, as we get more and more advanced sensors that I will show examples of, we are basically getting more and more knowledge about the underlying earth conditions and where we can, expect to have a mine. There is also a problem, and this is a case also in Australia, that many of the mines that are being explored, they are basically the ones that have provided a lot of profit. And as they run out, we are looking for new places, and a lot of new places, they run deeper. So you need advanced technologies to be able to explore, to get insights and get the right intuition of where potentially is a good place to explore. The other thing is that AI can help provide analytical modeling, provide an indication of where you can improve efficiency, where there are profits that are being lost, where some optimization can be done to the workforce to improve the final yield and profit. So it can be used in analytical and in terms of explaining the current situation. it's also useful for maintenance. So as you saw in the video, there are a lot of moving parts for a modern mine. You have a lot of equipment, and a lot of them are really expensive, and they have to be regularly maintained. So if you don't maintain them well, you can incur a very high cost. The other problem is that when one of these machines break down, as you saw in the video, the whole circle, the whole complex pipeline that depends on delivery of each individual component kind of fails. So if you have a right estimate, so in many cases they don't mind maintaining or maintaining their equipments earlier, but it would be a huge cost if you are, so that would be a very marginal cost. But if you are making a wrong prediction, or if you are missing part of this machinery that has been faulty, then the cost would be catastrophic. The other area where you can think about utilizing AI is in operations. As you saw, for example, you have a lot of trucks and a lot of a lot of equipment for moving the ore from the mines, and a lot of that can be autonomized, and we will look into a few examples. And finally, the insight communication that we touched upon, where you can help the experts and improves part of their work process. We will look at an example later on, but in many cases, a lot of this processing of the sensors, it has been done manually. Obviously, computer helped a lot, but still a lot of these processes are time consuming. It relies on simulations that are based on a lot of assumptions, physical assumptions that in many cases are unrealistic. So improving any part of those processes can have also huge impact. So let's look at a few other examples where it has been autonomous AI has been utilized or has the potential or being investigated for employment in mining industries. As we move forward, we see more and more examples, local examples in Australia, because it's a very important industry in Australia, and its success or failure can have a large impact on the whole country. So let's look at how AI can help with autonomous trucks. It also gives you a context of what trucks in mining would look like and how they operate.
The autonomous truck pilot was initiated in June 2013 with only 3 trucks at Jimblebar. Today, we're 50% autonomous operations, and I'm very pleased to announce that we received the approval that by December, we plan to be 100% autonomous trucks.
Automation in the mining industry is going to be important. It's good for safety, putting people in less dangerous positions, I guess. It's predictable. We can see exactly what the trucks are doing all the time. We're telling them what to do all the time.
And we have good systems within our vehicles, and it can show us the predicted path of all our trucks. It can predict possibly an interaction, and it will prevent that from happening way before I think the manned vehicle would even realise it.
If something is put in the way of a truck, essentially what it'll do is there's a LiDAR system that's on front. You'll see that in any Google car as well, same sort of technology. And what it'll do, essentially, it'll pick up that there is an object in front of it, and also too, there's a radar system in the front as well. So if it picks up an object, it's roughly got 20 seconds once it picks up that object, that if it doesn't move, then it will stop and it will send an alert to the controller.
By definition, the safety controls with the LiDAR and the radar and the predictive path technology with GPS is making the operation safer from an interaction point of view.
Yeah, I mean, the last thing we ever want to do is hurt anybody. And I'm very confident out there in the field
working around the trucks. I feel safer than maybe a manned operation. It just blows you away every day how clever it actually really is.
So obviously that eliminates us from being in the mining area itself. So a lot of faults we can diagnose from the office. We can make those calls and then come out. We can get a truck in a safe location and then carry out the repair from there.
We collect a lot of data from these trucks that allow us to optimise truck paths, corners, ramps, load zones, dump zones. It allows us to really understand in depth how the truck is performing within every component of the cycle. It really allows us to drive improvements by understanding exactly where the trucks are slowing, where the trucks are operating effectively. It allows us to create some standards about how do we improve the way we operate.
It's a safer way of mining. It's reducing the risk for people. It's giving people opportunity to upskill and go in a different career direction.
For me, it's been a good opportunity to turn my hand to something new. We've been doing the same thing for quite a few years, so it's good at something a bit different. And it gets the brain going.
You know, normally you could expect to sit on a truck for years before you get to train up on some different machines. You come across here, pretty much the training starts straight away. So we need you to be able to drive a loader, dozer, ITs, whatever it may be, because there's no more trucks.
I'm Stephen. I've been here 1.5 years. Started as a trainee haul truck driver. You know, I'm now loading trucks and pushing dumps and getting the other side of mining behind me. And
it really enables the development and the upskilling of our current workforce to the point where there'll be industry-leading operators into the future, enabling their own personal skills and career development to continue. I think for me personally, that's a really promising story for autonomy in our site and the way we've gone about the implementation.
We've got a guy here that's about to get up his 30 years with BHP. You can imagine what mining looked like to him 30 years ago, setting foot down in Whaleback. And now he drives around an LV using a computer system to manage a virtual mine model to make the trucks go faster, take corners nicer. So I just think about that bloke, and that sells autonomy for me. You know, that's awesome. Like, I love that. That's why I like that.
In the 21st century, technology development and innovative thinking are key to how we do business. Accelerating the pace of innovation will increase Suncor's operating efficiency and lower our costs. This is fundamental for our long-term sustainability. Sometimes we aggressively lead research and development of new technologies, but sometimes we collaborate, leveraging and advancing the work of others. One such collaboration involves autonomous haul trucks. Komatsu has developed technology that allows safe and efficient operation between manned mining equipment like shovels, graders, and dozers, and autonomous haul trucks.
Basically, what it does is puts a control system on the truck, and then a computer control room controls where those trucks go and how fast they go and how they operate. The technology has been deployed in other parts of the world, primarily in Chile and in Australia. That's really what we've been working on for years, is to try and figure out, can we take that technology and apply it to a soft rock mine where we have snow and rain and those sorts of things. So that's been the entire focus of our efforts. And so now that we've done the work, we're very confident that we can safely deploy this technology in our environment. An autonomous haul truck needs to know three things: where it is, where it needs to go, and what to avoid. And there's GPS on all of the equipment in the mine, so that the system at all times knows where each piece of equipment is in space and relative to each other. So trucks only travel along predefined courses to assigned destinations. A supervisory system manages the safe movement of trucks using onboard systems and GPS information provided from all vehicles in the mine area.
AHS technology offers several potential opportunities: enhanced safety performance, better operating efficiency, lower operating costs.
But moving towards autonomous technology doesn't mean moving away from people.
Like almost any technology, the technologies do have an impact on workforce. In this particular case, we change our workforce and we end up with different skills. We're helping and working through with employees on the transition of the workforce associated with this. There will be some people that will be impacted, and we're working through now is exactly how that will work.
Following a successful commercial scale evaluation, Suncor is proceeding with the phased implementation of AHS, starting at the North Steepbank Extension Mine. Based on current mine plans, we expect full AHS implementation to take 6 years. Doing this will involve deploying more than 150 autonomous haul trucks.
So can see how basically different stages these different companies are and how they plan differently on approaching the problem. Right, this is another interesting area where autonomous driving has been able to help. For example, when you have a lot of machinery that are in remote.
Hi, Sam, I think we lost your screen, so your networking is quite slow, I think. We have some delay.
Can you see the screen now?
No.
Let me turn off my video. Maybe
Yeah.
that,
And try to reconnect it, okay?
Yep. Can you see now?
No.
That's
Maybe you quit and join us again and try. Yeah, I think Asa has some connection problem. Yeah, he's in. Yeah, we can say it now. So maybe Asa, can let's have a break. So it's 2 o'clock now. So let's come back 2 and 10. Is that okay? Hi, Asa, can you hear me?
Yep.
Okay, so let's come back. So Essen, can you try to share a screen now?
Can you see my screen now?
Yeah, that's it. Thanks.
Okay. So the other aspect that we can use AI is basically sorting of the input, sorting of the ore. So this is an example of an AI system or an autonomous system that's being used for drilling and filtering the ore. Okay, so now we look into an aspect of the problem that we have worked on as well a bit, which is exploration. So a great deal of work has been done on the essays, on the information that you can collect from geological and geophysical aspect of the Earth, of the crust of the Earth, and that's a key in understanding where we can find minerals that we are interested in. It's also important to note that really drilling, so you can't really have a hunch and go drill a place. Drilling costs around $500,000 to really get the actual sample of where, for example, you think there is gold, if there are really gold in that place. So we have to be very strategic in designing and deciding where to drill. So let's look at the data that's being collected. This is now a bit more local. So we're looking at data that's being collected specifically in South Australia.
Australia's share of mineral exploration expenditure has halved from approximately 1/4 to 1/8 of the world's total during the last 20 years. This decline has paralleled a decline in the discovery of new major mineral deposits in Australia. Decrease in mineral exploration success and expenditure in Australia reflect the fact that relatively easy to find mineral deposits with a surface expression have largely been discovered. New mineral exploration provinces must be found beneath barren cover rocks. The Mineral Systems Drilling Programme is undertaking extensive drilling aimed at both revealing mineral exploration provinces hidden by barren cover in the highly prospective Eastern Gawler Craton of South Australia, and at developing the new technologies required for ongoing, cost-effective, successful mineral exploration beneath barren cover.
The Mineral Systems Drilling Program is a world-first collaboration between government, in this case, the Government of South Australia, industry, with industry partners such as Kingston Resources and Minotaur Exploration, service providers such as Boart Longyear and Index, and then also researchers, particularly through the Deep Exploration Technologies Cooperative Research Centre and its partners in universities, CSIRO, and other government surveys. This collaboration brings together an enormous amount of funding and in-kind support. It's now a program with over $7 million, $2 million of which comes from the South Australian Government and its PACE Frontiers program. A further $1 million comes from the industry participants of Kingston Resources and Minotaur Exploration, as well as from the DET CRC.
The reason the Mineral Systems Drilling Program is so valuable to Kingston is it combines the resources of government, the knowledge of world-class researchers, cutting-edge technologies, and the nimbleness of a focused mineral exploration company to bring a truly multidisciplinary approach to the challenge of exploring undercover.
The Gawler Craton in South Australia offers one of the greatest geological exploration challenges in the world. The prize is great. It's one of the most prospective parts of the Earth's crust, but the challenges are also great. The area has deep and widespread cover.
Minotaur's been active in the Gawler Ranges area for a number of years, but we've never fully understood the mineral system model that's active there. This DSD mineral mapping program gives us a fantastic opportunity to accelerate that program.
This Mineral Systems Drilling Program is addressing that challenge, firstly by putting drill holes into that exploration frontier. The other way that we're doing that is to bring state-of-the-art technology into that drilling program to increase the efficiency of meeting the challenges in those covered areas.
During the Mineral Systems Drilling Program, we'll trial several world-first technologies developed by the DET CRC, including the wireless sub, the autosond, and the lab rig. The wireless sub will monitor drilling parameters, sampling at a high frequency, which will enable monitoring of the drilling process and the interaction of the drill rig with the rocks in real time. The autosond is deployed in the drill hole after drilling is completed and logs while the drill rods are removed from the hole, providing geophysical data of quality comparable to wireline logging techniques. The lab rig measures geochemistry and mineralogy using XRF and XRD techniques on drill cuttings returned to the surface during drilling. Data from all DET CRC technologies can be delivered in near real time via satellite communications anywhere in the world to enable better decision making during the drilling process.
So one of the aspects that really makes this a very timely place to look at exploration in especially in SA is that this type of data is collected, and as you can see, it comes from a lot of investment into really understanding how the Earth crust, at least in South Australia, work. And a very good data source that we've looked at is called SAREG. And it has also, as part of this project being collected, and it has a lot of geology and data about this drilling information, and a lot of good data that can be utilized for understanding better where to explore. So let's look at how this data is being collected and how what kind of information it has.
South Australia is a region rich with resources and the critical commodities of our future. In an age where data is essential for understanding our planet, the gateway to exploration in our state is the South Australian Resources Information Gateway, SARIG. As the new frontier of data technology, SARIG is a leading-edge portal of digital online maps and information, covering more than a century of mining exploration. It is playing a vital role in helping unearth the growing number of discoveries and highly successful ventures developed for industry, research, and the public. It provides global access to South Australia's key geoscience, mining, petroleum, and exploration project information, and offers a streamlined portal to do business. SARIG is an intuitive tool that is free to use and download, with no login or software required. In 2019 alone, there were around 2,000 users a month over 110 countries who viewed 700 geospatial datasets, recorded almost 61,000 sessions, and made more than 200,000 API service requests. As a single entry point to 12 separate databases, users can find and download open data on where significant activity is occurring, or type interesting hotspots and access extensive information around project findings, drill sites, geology, and prospective areas. Investors can explore investment opportunities through SARIG's world-first commodity dashboards and resource industry statistics like exploration, production, exports, and employment can be found on the Mineral and Petroleum Industry Indicators dashboard. With the ability to save and export map capabilities, allowing retrieval from multiple devices, and sharing on social media channels, SARIG takes exploration to innovative new levels in Australia. To start exploring, visit map.sarig.sa.gov.au.
So we have another complementary data set to SARIG that basically has a lot of geoscience aspect and a lot of drill hole data. It's called GCAS, and I won't. Basically, there is a video that you can see. You can fly planes across South Australia, and it's a very interesting technology that can collect a lot of data about the gravity of the gravity, which is, as opposed to what we usually think that it's constant. It basically, depending on the type of minerals that you can have, it could change, and there are very interesting sensors that when the plane flies over, it basically detects where the gravity is lower and where it's higher. You could think that if it's higher, it indicates that you have a bit more heavy elements, such as iron, for example. So a lot of that has been collected, and there is a nice data set that we can access, and it's very helpful for a lot of things that we have also done. So we've looked at basically this data set, basically a combination of SARIG and GCAS that provides drilling information. So we looked at two general solutions for two consecutive years. So one was we looked at the geological information, basically rock types, and a bit of gravity information. There are different sensors that you can collect data for. And what we did was we looked at those geological information and geophysical information and predicted where the drilling holes could be. And from that, we built basically a heat map. So this is a summary. So this was the first version that we did in 2019. So there is this summary. I hope my internet connection can help, and you can see kind of the gist of what was being done.
Second place, congratulations to Team Zone X.
I've been a passionate mineral explorer for 43 years. Discoveries are now becoming harder as we look deeper and rely on myriads of data trying to detect new ore deposits. So I am pleased to be returning to the university to work with the Arvins team as a domain expert for the Oz Challenge.
There's the Australian Institute for Machine Learning, located at the University of Adelaide. It's one of the world's best machine learning groups, and in particular, one of the largest machine learning groups in Australia.
We can formulate the problem of mining exploration as a computer vision problem because of the availability of GIS data in raster format. So you're effectively getting a measurement at different locations. So you're measuring specific gravity or magnetics or something like that. We can represent this as an image and then apply computer vision techniques to the problem.
The main challenge of this project is the lack of training data. So we use state-of-the-art machine learning approach. And we know this kind of approach is data hungry.
But now that I've analysed this data in 3D, I have deemed it as probably not worthy of inclusion in a specific 2D study of this nature. But however, it may provide great relevance in the subsequent study in the Mount Woods region.
AI is also very good at absorbing humans' domain knowledges. Those knowledges are accumulated for 1,000 years, will be wasted if we throw them away.
We believe there is a future potential of deep learning on mining area. I think this is just the beginning of the journey.
It seems to me that what's happened in this instance is that there's been fantastic agility. There's been people who've seen an opportunity and have just gone for it. And far too often, we're unable to do that for whatever reason in the university. This is the beginning of something, and there will be a lot of interest, so we'll be fighting a lot to once people know a bit more about us, they'll bang on the door.
This is the start of a much bigger enterprise rather than the end today of the beginning.
It is the beginning of a new approach to new exploration, and a really exciting one in which Adelaide has put itself at the centre.
I was delighted to see how machine learning gradually produced iterations of the predictive models and started to forecast things which I could see as a seasoned explorer.
I'm really proud of what they achieved in the last 3 months. You come to my call with the school flag and without these guys, this would be impossible. And we knew nothing about mining before, but we had the best to handle it. And we achieved so far, and I can't wait for the future to come.
Okay, so the first version wasn't really, it was a great start, but we needed to be able to do a bit more than that. So in the second year, what we looked at was basically 2 scenarios. One of them was looking at the current experts pipeline and workflow and improving their workflow, trying to assist with some of the parts that would take weeks to complete. And the other part was kind of to enhance this end-to-end model where you have raw data coming in and you can predict basically particular elements or particular geology. So this is the summary of what we did for the second year.
DeepSetX presents to you several machine learning models that utilize some of the best AI expertise and domain knowledge.
The Golden Craton in South Australia is a vast region of
ancient basement rocks, which is host to many world-class mineral deposits. The problem when exploring this region is that most of the area is covered with young sediments which obscure the ancient rocks. So we need techniques that help us see through the rocks to improve the exploration prospects for explorers. We can use this with remote sensing techniques. One of these most well-known remote sensing techniques is geophysics. We use techniques called gravity and magnetism. These are collected through land or airborne types of surveys. Over the last few years, the South Australian government has flown a vast airborne magnetics exploration survey called Bulla Cradle Airborne Survey. We're going to use this data along with gravity data to help us peer through the cover and find out what's underneath. The problem with geophysical interpretation is that it is not unique. We need additional information that can help us constrain the interpretation in a more refined way. We can use machine learning and deep learning techniques such as that offered at the Australian Institute of Machine Learning here in Adelaide to help us find these interpretations in a more systematic way. This can help us link different types of mineral discoveries with geophysics and geology and machine learning together to create an integrated product.
We have developed an explainable deep neural network model that receives gravity anomaly and magnetics and two of their derivatives as input and produces ternary domains as the output. This is the first step. For the next step, we combine T-domain predictions with the 4 channels of input again and produce pseudo-geology interpretations.
We have a mineral segmentation model that takes the GCAS as input and the output is a per pixel mineral distribution over the globe. This was trained using the SARI global data.
Deep neural networks have been the driving force for artificial intelligence applications in many domains, including mining. In this challenge, we take the deep neural networks a step further and incorporate attention mechanism. Attention allows our models to be more accurate and explainable. This attention mechanism gives us the ability to interrogate our model and explain which regions of the input contributed to the predictions of particular minerals, and which means we can create heat maps of the input and look at the regions that are important for our predictions.
We created a model that extracts information from the lithology assays that then provides a per pixel distribution of the rock types.
Because we have per pixel level distributions and also segments, so we can aggregate those information within each segment to provide tables of attributes.
I fully endorse the team's goal of using potential field data to produce more detailed pseudo-geology maps in covered areas. I took a backseat role this time as a geological advisor, but once again enjoyed working with young data engineers adapting their skills to mineral exploration.
This is the beginning of AI for mining, and we are looking forward to the future to come.
Okay, so this is the region that we looked at, and the way, so that was basically the general picture of what was done, but a bit more detail. Now we can look at the region that this project was done on. So it's basically this Gawler region. We extracted, basically defined 16 regions, and based on the standard that was defined on GCAS, and which is the standard that's used in that data set, and then we split that data set to basically patches of information that we're looking at, similar to patches of images. So each patch is 12 square kilometer, and we basically used the gravity as well to augment the that data set. So it's basically like a transformation on the gravity. So we looked at the minerals in the output. So this is the one of the cases that we looked at. So if you look at basically this SARIC data, it has minerals, different minerals that are detected at each point where it was derailed. And what we did was we sorted them based on frequency. So frequency and of course interest. So in the regions that were explored, for example, gold and copper, they were the most frequent minerals. We also collected some lithology assays, which are the information about the rocks, the rock types, and for that we basically took the advice of the domain experts. So you can look at so we can cluster, in a sense, or group these different geological aspects into 9 groups. So these are again based on the experts' recommendation that some of these rock types basically are categorized together and have the same kind of indication in terms of the minerals that could be found in those places. So we used magnetic and gravity, which are very interesting type of data that could be explored in this type of in this type of problems. So as I mentioned earlier, in a lot of these problems, you need a lot of data cleaning. So even though GCAS has done the cleaning, the initial stages of data cleaning, but it still needs a bit of cleaning and normalization. So what we did was, for data cleaning, we performed interpolation. So we filled the unknown values with interpolated values as an estimate of what potentially those missing values could be. We did a normalization for each channel. We looked at basically normalizing data to have a 0 mean and a unit variance, and basically we got this type of data. These are basically, so you have gravity, you have radiation, and these are the other type of collected data from different sensors. So this is for one of the regions. We've performed data augmentation, which is kind of standard. We did a bit of rotation and a bit of shearing and a bit of translation to improve the data, the number of instances of data that we have, because in these scenarios, as you can see, that even though the volume of the types of data are huge, but relatively for a given region, you don't have a lot of data. So it's good for increasing the number of instances. So for one scenario, we looked at the experts' work process, and what it meant was, so this is the work process where the expert basically takes the gravity data and converts that to something that's a bit more interpretable, a bit more understandable. And that process, just taking gravity and making gravity something that's a bit understandable, takes month of work. So we went through a 3-stage process. So this is the 3-stage process that the experts also go through. So they take the gravitational measurement. They basically split up into different regions of anomalies or different structural classifications. That's what is called the T domain. And these T domains represent different classes of gravitational characteristics. Then these T domains are collected collected and aggregated together, and finally we use a neural network to predict the geology or mineral characteristics of this this distribution. So humans usually human experts usually look at them and say, okay, based on this type of gravity, there is potential for this type of mineral, for example. So for gravity to be transformed to a continuous as a continuous value to a discrete value, which is a bit more understandable, the domain experts look at something similar to the gradient of these gravities. So this is a raw gravitational data. So it's a bit processed with this Bouguer gravity, but it looks like it doesn't really mean a lot. So it's hard to understand what it means. But what this process tries to do is that convert that to something like this, where different color codes can represent different aspects of the geology there. So these are basically different polygons in a sense. Each polygon represents different rock characteristic. So this this continuous space here on the left to this discrete representation on the right, this is where you get the polygons for different areas where they could have similar gravitational characteristics or potentially rock and mineral characteristics. So you can see that it usually shares some aspects of the color. So what we can do to automate this is really to do a simple clustering on the colors. So group the colors that are more similar together, and from that the experts would be able to look at those colors and really interpret what it means. For example, if you see red, it means that it's a it's a plateau, for example. Or if it is green, then they would say, okay, it's a dome. And if it is black, it's a plateau. So different colors have different meanings. And so for the whole region, we can get a picture like this that represents, so reds were plateaus, so a lot of plateaus, but then these different colors in between, they represent different anomalies that could potentially indicate that there is something to be explored there. So we have the software that's developed for this. I'll skip this, but basically there is a software that you can look at different layers of how these different characteristics are being combined and used. So what? This is what the experts would go through. So they would take the raw data that we saw. It looks like a black and white data, and you can have different aspects of it or different processing mechanisms to get different versions of the data. So you have different channels as those data, and in the output after that processing that goes through basically first making it something colorful, and then from that getting these clusters and polygons. We try to automate that part. So we put in all that gravitational information into a neural network. So in this case, there is a ResNet, there is basically a tension in between, and from that we try to predict for each pixel what that polygon really represents, from what the experts could have done with their own tedious and computationally expensive process. And we try to replicate that with a neural network so that for other regions, if you get the same gravitational data, you can really predict these polygons without really going through that process that's the conventional process. So we can look at an example of, so this is one example of one particular patch as the input, and one particular patch as the input, and we have attention as I mentioned in the input for better interpretation. So this could potentially represent the attentions, the right heat maps represent the attentions on this input. And what it means is that there are, for example, red regions that indicate, for example, indicate a particular characteristic. So the network looks at these regions to predict the different polygons. So this is an important aspect, for example, in the input. So this anomaly is an important anomaly to look at. So the experts will look at it with more details. And this is when that heat map is mapped onto the output. So you can see that you see a lot more detail and a lot more complexity in these predictions. So this is where so the second approach is really what us as AI experts would look at, basically taking data as the input and predicting what is important for us. For example, mineral classification is important. So what we do is that we take the input as what we can collect from these regions, and then predict the minerals and in the output that we are interested for. So for that, we split the data set into the training, validation, and testing. And obviously, we chose some regions that are more regions for training. So some regions that are distinct from the validation and test set. So we train on the red region, we validate it and optimize our hyperparameters, and then later on look at how it performs on the test area. So this is an example of the input that we saw. So we get basically the same sort of gravity and the other magnetic and the rest, the type of inputs that we can get from GCAS, and put that through a neural network that predicts where you can find what mineral. For example, AU, which is gold. We look at each pixel and say, in the output, what is at which point we can expect to have how much gold. So in this example, we cast the problem as a classification. So at each pixel, we look at if there is gold or not, no gold. And you can see that basically the model can predict that there are some regions that there is a high probability of finding gold. So the network architecture is very similar to what you would have as either an autoencoder or a segmentation problem, where you take the input and then the output is prediction of basically the presence of the pixel element for each pixel. So these are examples. For example, this is the heat map of where potentially gold could be found for the whole region. So we can use that data, the same algorithm basically, to predict the geological aspect as well. So for that, we use kind of the same architecture, but in the output, instead of predicting if there is gold or the other minerals, we look at different geological groups that I introduced earlier. And this is helpful because for the experts, it's important to understand what's going on, and they want to have a good model to tell them at which region, with some of the measurements, especially these measurements that you can get with airplanes, how likely it is that they find particular geological formation, and that geological formation basically tells them what kind of mineral they can expect to find there. Would it be hard to get access to it? How deep it potentially could be, and a lot of other information for the geologists. So this is an example of how the model basically predicts these different types of geological outputs. And another thing that we looked at was that basically, rather than looking at gold and saying if gold could potentially exist at some place, ideally what we want to look at is this 3D map, because you could have gold, but it could be in different at different depth, and that depth is important for these industries, because that's how they would evaluate how much they have to put in, how much money would that cost to really reach that mineral, and then they could basically do a risk assessment of if it's worth it or not. So we are looking at basically extending this method for this 3D mineral prediction, where you can basically predict from these measurements what is the underlying formation of either rocks or minerals. So you can, in summary, you can basically put in the raw data in form of gravity and other form of data that we have. You can either go through an expert process, take the expert augmentation process, where we take, the expert's existing process and try to enhance that with our methods. We try to replace part of that or facilitate part of that. Or we can go through a fully data-driven end-to-end approach, where we perform a bit of operations, but we train a deep neural network to go from that gravitational, the gravity input to the actual predictive values that we are interested in, for example, minerals or geologies. So we change gear a bit, and I'd like to quickly go through another application that we looked at, and it's in maintenance. So we mentioned that trucks are very important in once a mine is discovered, in terms of extracting ores from these minerals. Trucks are very important, but their maintenance is a very and scheduling that maintenance is very important. So one thing that we looked at is, can we use the sensory data that we collect, that these industries already collect from their trucks, to really have an estimate of when is the best time to perform certain type of repairs or maintenances. And the problem, and with these methods, we really need to basically be able to estimate what is the activity that the truck is doing. Is it delivering? Is it dumping, and what path it's going? And usually the algorithms that humans design are not really accurate. So it requires a bit of more processing. So I skipped that, but just quickly, we look at the sensory data that we can collect. So we have like 500,000 with a company that we worked with, and it basically captures the truck's activity, and it kind of inform us about, or tell us about the health of different aspects of the equipment. So when it's connected, in this case, it's unannotated. So we need to annotate them. So one simple annotation that we look at here is just to basically look at if that signal really can tell tell us about what activity is the truck doing, and that gives us an indication of if it's performing the tasks in a timely manner, and which part could potentially be faulty. So this is a signal that you can collect, for example, or we could get from a load event. So as you can see, this is the strut pressure. As you can see, and as you expect, as you basically dump or load a bit more into the truck, it increases, and as you dump the load out, this basically decrease. So we looked at if a neural network would be able to predict these dump or load. And we basically designed a convolutional neural network, and it's basically pretty accurately can predict if what activity a truck is doing. And it's very important because it gives you a picture of what the mine is, what is going on in the mine, and where, because you can combine that with the GPS data, you can really look at where each truck is and what activity they're doing. So these are two examples of them looking at dumping and loading. So the same kind of technologies can be used for oil and gas. In oil and gas, many aspects of the problem are the same. And one of the things that we looked at was the reservoir prediction. And it is important because it controls the pressure, and it controls and it gives you an estimate of how far you can go and what you can expect to extract from a reservoir. So traditional methods basically are computational models that are physics-based, and they're very expensive, they're very slow. And what they try to do is that they try to put the actual input in. They try to make a lot of assumption about the model and tell you about, based on the physics of the flow, how much you can expect to extract from an oil reservoir. So one thing we looked at was basically if we can train a neural network to simulate these simulators and hopefully the real world problem. So we gathered a lot of different scenarios from different reservoir systems, because based on the geology, you can really have different systems. And then you can train a model which captures all these different aspects and different types of reservoirs. So this was very interesting, and it was very positive in terms of really using a simple neural network that can reduce the operations that these simulators now take days to do into few seconds to tell you about how much you can expect your reservoir to produce in a given time. So I think I break here. I stop here. I had another example to go through, but I think given the time, I would stop here. So if you have any questions or any concerns, please you can either use the chat, or you can email me, and I'm happy to respond.
Yeah, thank you, Eason. So it's a very great talk, and you show us many examples. I think this is a typical good example and a great success of using machine learning on some real industries like mining, right? So yeah, I think Julian asked one more question. Can you try to answer this question? Yeah.
What is the advantage of using the in comparison with traditional time series analysis? So you can utilize time series here as well, but the advantage of neural networks was that it was quicker. You can do it basically kind of online, And in terms of performance, it performed really well. So that was one of the reasons that we use neural networks. But you can look at other approaches as well, for sure. So you can do time series estimation, for example, for that. But yeah, neural networks usually provide more accurate solutions.
Okay, thank you, Essen. So if we don't have more questions, I think this is the end of our today's lecture. Thank you again, Essen. So this is a great talk. Yeah, can you stop sharing screen? I have something else to tell our students.
Sure. Yeah. Thank you.
Thank you.
Thanks for your invitation.
Okay, so. Okay, one more thing I want to say is about the workshop this week. So we have two workshops this week. Well, both of them are exactly the same. So the first one will be on Thursday, 1 p.m. to 2 p.m. This will be an online session because we still have lots of remote students. So I will have an online session, so which will be on Thursday. And on Friday, we have a face-to-face session, which is from 11 to 12. It will be in EM ground floor 7. So you can choose either one. So the contents will be exactly the same, but you can go to online, or if you want to be the face-to-face, you can go to the campus. And be careful. So so if you go to campus, you have to wear a mask. Okay. So that's it. And if you have any questions, you can send me an email, or just post on the discussion channel. Okay, so let me see IBM options. Yeah, so it doesn't matter which one you enrolled before. For example, I know when you enroll this course, you may choose Thursday or Friday. It doesn't matter. Okay, so if you want to go to online, just go to Thursday one. Go to the online one. If you want to attend the campus one, just go to the Friday the physical session. It should be fine. Okay, no, it doesn't matter which one you choose before. Okay. Okay, that's it. I will stop sharing my screen. Okay, again, thank you very much. If you have any questions, let me know. And yeah, this week we have 2 workshops, and next week will be our just the technical session, and I will tell you more about the basic technical details about the machine learning. Okay, thank you very much. Have a good day.